Hi, we are engineering brothers, and once again we have got our another interesting problem for our torque voltage analogy additional problem 3 over here, and you can see that this is our conventional mechanical rotational system over here. And in this case we have applied the torque at the right hand side for our diagram. You can see that. Now if you do apply the torque at this point, we have got the angular displacement of theta t that has been happened over there, and because of that disturbance, the J1, the common factor in between our theta 1t and theta t, these two elements of rotational spring K and the rotational frictional element of B1t is getting disturbed by that applied torque at the right hand side for our given diagram, and because of the disturbance the rest of the body will get disturbed by that applied torque at the right hand side for our given form of our mechanical rotational system over there, and the J2 is getting disturbed by that one, and the B is also disturbed by that consideration over there. Now if you do apply the torque at the extreme side for our consideration, so the whole body for our mechanical rotational system will get disturbed by that consideration. Now we are going to consider the same approach just by follow up the same procedure over there. So our first step will be quite naturally, first we will draw the nodal diagram just by looking at this given conventional mechanical rotational system over there. So to do that, we do require to mention first, or need to note down first, the angular displacement part over there. So in our extreme right hand side we have got the theta t, and in this side we have got the theta 1t, which is been placed over here. And let us see what are the elements that are connected with this angular displacement factor over there. So in our extreme right hand side we can see that the J1 is been present over there. So let us do include the J1 over here. So this is our J1, and in between our theta 1 theta t, and in between our theta 1t, in between our theta t and theta 1t we have got two elements of rotational spring element of K, and our B12, which is our rotational frictional element, that are been present over here. So let us do include our two elements of our first element is our K. So this is our K, and with that one we have got the B12 that is been present over here. So this is our B12 that is also been present over here. So this is our B12. Now let us move on towards our left hand side for our consideration. We can see that with the displacement, or with the angular displacement of our theta 1t, the J2 has been associated over here. So let us do include our J2 over here. So this is our J2, and the last consideration is our dashpot element, which actually indicate the rotational frictional element over there. So let us do include that B as well. So this is our B. You can see we have included that factor as well. So this is our B, this is our J2, and with that one we can say that the J1 is been completed over here. So I want to repeat this portion once again. If we do apply the torque at this point of our theta t, so let us do include the torque at this position over there, because we can see that because of that applied torque, the angular displacement factor will be there. So the torque will be applied at this point. So this is our applied torque. Now let us do check whether our diagram is right or wrong. So if we do apply the torque at this side of our consideration, the angular displacement will become theta t. So let us find out what are the elements that are connected with our theta t. So first I can see that the J1 has been connected over here, and quite naturally in between our theta 1t and theta t, the two elements are placed, or that is been connected in parallel over here, which is K and B12, that are been connected in between our theta 1t and theta t over here. And quite naturally, if you go for the rest of our consideration with our theta 1t. The J2 has been connected over there and the B has been connected in this given consideration over here. Now we have to include the torque at this right hand side for our consideration. So this is the much needed conventional nodal diagram over here, and I can say that this is our node 1 and this is our node 2. Now in our next step, if you do apply the D'Alembert principle on our node 1, what is going to be the equation? The equation will be this one: the applied torque plus of a resistive torque, the summation of these two torque, or the summation of these two opposing torque, will become the 0. So this is our equation, first equation. And if you do apply the D'Alembert principle at our node 1, the equation is going to be the applied torque minus our resistive torque. So what are the resistive torque element that are connected at our node 1? The resistive element will be our J1 d2 theta t divided by our d theta 2 plus our, so as these are all our resistive elements over here, so the magnitude of all this resistive element will become our -1. So this is minus. Now go for the common part for this consideration. So first I will take the spring element. So spring multiplied with our the resultant displacement, as we are taking 1 as our reference for this consideration. So the resultant angular displacement will be quite naturally our theta t minus of our theta 1t over here. So this is our next equation, and for that next equation we are going to consider the v12. So minus v12, and the equation will be d dt. And let us go for the same resultant angular displacement over there as the same one, as we are taking the theta as our reference factor for this consideration. So the equation will become our theta t minus of our theta 1t, that is ultimately equal to 0. So this is our first mechanical equation over here after I have applied the D'Alembert principle at our node 1. So I am just going to repeat this portion once again. If you do apply the D'Alembert principle at our node 1, we have got this is our equation. So applied torque minus of J1 d2 theta t divided by dt2 minus of, now we can go for the common part for this consideration. So first I will go for the first common part of our k, which is minus k, and that will be multiplied with our resultant displacement in this connection. And why do I consider the resultant displacement? As you can see that the k element is being present in between our theta 1 and theta t over here. So quite naturally, as we are taking 1 as our reference for this consideration, that is theta minus of theta 1t, that is our consideration. In our next part we have got minus, and similarly we will go for the frictional element of rotational dashpot element that has been present as our b12. So that will be b12 ddt of our theta t minus of theta 1t, which is equal to 0. So this is our first equation after we do apply the D'Alembert principle at our node 1 over here. Similarly, we will go for the next equation just by applying the same procedure. Apply the D'Alembert principle at our node 2, then the equation will be this one, which is minus J2 d2 theta 1t divided by our dt2 for this element, and for that next one we do have minus b d dt of our theta 1t, and minus now we can do consider the common part over here, which is minus k. And in this case, as we are taking 2 as our reference factor in this consideration, then the equation will become this one, which is theta 1t minus theta t, and finally minus, we are taking the next common factor, which is v12, and the equation will become d dt of our, quite naturally, theta 1t minus of theta t, as we are taking 1 as our reference factor in this consideration, which is quite naturally theta 1t minus of our theta t, which is equal to 0. So this is going to be our second equation over here. Now if you do take the minus common from this whole equation and do transfer that minus to the another side of our equation, so all these minus will become plus. So this will be plus, this will be plus, this will be plus, and ultimately this will be plus. So after we have applied the D'Alembert principle, we have got these two equations. So this is our first equation, which we have named as equation 1, and this is our second equation, which we have named as equation 2. In our next part, we are trying to use or utilize our once again the chart or the analogous chart in between a mechanical rotational system and the electrical system, and we are going to utilize this chart to form or try to form the torque voltage analogy over here. So keep following my videos, and do like, do share my videos. So just wait for my next part.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.